But when we examine ordinary air very carefully, we find small quantities of other gases in it, besides oxygen and nitrogen. First, there is carbonic acid gas. This is the bad gas which we give out of our mouths after we have burned up the oxygen with the carbon of our bodies inside our lungs. And this carbonic acid is also given out from everything that burns. If only animals lived in this world, this gas would soon poison the air. But plants get hold of it, and in sunshine they break it up again, as we shall see in Lecture 7, and use up the carbon, throwing the oxygen back into the air for us to use. Secondly, there are very small quantities in the air of ammonia, or the gas which almost chokes you in smelling salts, and which, when liquid, is commonly called spirits of hartshorn. This ammonia is useful to plants, as we shall see by and by. Lastly, there is a great deal of water in the air, floating about as invisible vapor or water dust, and this we shall speak of in the next lecture. Still, all these gases and vapors in the atmosphere are in very small quantities, and the bulk of the air is composed of oxygen and nitrogen. Having now learned what air is, the next question which presents itself is, why does it stay round our earth? You will remember we saw in the first lecture that all the little atoms of a gas are trying to fly away from each other, so that if I turn on this gas jet, the atoms soon leave it and reach you at farther end of the room, and you can smell the gas. Why then do not all the atoms of oxygen and nitrogen fly away from our earth into space, and leave us without any air? Ah, here you must look for another of our invisible forces. Have you forgotten our giant force, gravitation, which draws things together from a distance? This force draws together the earth and the atoms of oxygen and nitrogen, and as the earth is very big and heavy, and the atoms of air are light and easily moved, they are drawn down to the earth and held there by gravitation. But, for all that, the atmosphere does not leave off trying to fly away. It is always pressing upwards and outwards with all its might, while the earth is doing its best to hold it down. The effect of this is that, near the earth, where the pull downward is very strong, the air atoms are drawn very closely together, because gravitation gets the best of the struggle. But as we get farther and farther from the earth, the pull downward becomes weaker, and then the air atoms spring farther apart, and the air becomes thinner. The chief reason why the air is thicker or denser nearer the earth is because the upper layers press it down. If you have a heap of papers lying one on top of the other, you know that those at the bottom of the heap will be more closely pressed together than those above. And just the same is the case with the atoms in the air. Only there is this difference. If the papers have lain for some time, when you take the top ones off, the under ones remain close together. But it is not so with the air, because air is elastic, and the atoms are always trying to fly apart, so that directly you take away the pressure, they spring up again as far as they can. I have here an ordinary pop gun. If I push the cork in very tight, and then force the piston slowly inwards, I can compress the air a good deal. Now, I am forcing the atoms nearer and nearer together, but at last they rebel so strongly against being more crowded that the cork cannot resist their pressure. Out it flies, and the atoms spread themselves out comfortably again in the air all around them. Now, just as I pressed the air together in the pop gun. So the atmosphere high up above the earth presses on the air below and keeps the atoms closely packed together. And in this case, the atoms cannot force back the air above them as they did the cork in the pop gun. They are obliged to submit to be pressed together. Even a short distance from the earth, however, at the top of a high mountain, the air becomes lighter because it has less weight of atmosphere above it, and people who go up in balloons often have great difficulty in breathing because the air is so thin and light. In 1804, a Frenchman named Gay-Lussac went up 4.5 miles in a balloon and brought down some air, and he found that it was much less heavy than the same quantity of air taken closer down to earth, showing that it was much thinner, or rarer, as it is called. And when, in 1862, Mr. Glaisher and Mr. Coxwell went up 5.5 miles, Mr. Glaisher's veins began to swell, and his head grew dizzy, and he fainted. The air was too thin for him to breathe enough in at a time, and it did not press heavily enough on the drums of his ears and the veins of his body. He would have died if Mr. Coxwell had not quickly let off some of the gas in the balloon so that it sank down into denser air. And now comes another very interesting question. If the air gets less and less dense as it is farther from the earth, where does it stop altogether? We cannot go up to find out, because we should die long before we reached the limit, and for a long time we had to guess about how high the atmosphere probably was, and it was generally supposed not to be more than 50 miles. But lately some curious bodies, which we should never have suspected would be useful to us in this way, have led us into the secret of the height of the atmosphere. These bodies are the meteors, or falling stars. Most people, at one time or another, have seen what looks like a star shoot right across the sky and disappear. On a clear starlight night, you might often see one or more of these bright lights flash through the air, for one falls on an average in every 20 minutes, and on the nights of August 9th and November 13th, there are numbers in one part of the sky. These bodies are not really stars. They are simply stones or lumps of metal flying through the air and taking fire by clashing against the atoms of oxygen in it. There are great numbers of these masses moving round and round the sun, and when our earth comes across their path, as it does especially in August and November, they dash with such tremendous force through the atmosphere that they grow white hot and give out light, and then disappear, melted into the vapor. Every now and then one falls to the earth before it has all melted away, and thus we learn that these stones contain tin, iron, sulfur, phosphorus, and other substances. It is while these bodies are burning that they look to us like falling stars, and when we see them we know that they must be dashing against our atmosphere. Now, if two people stand a certain known distance, say 50 miles, apart on the earth, and observe these meteors and the direction in which they each see them fall, they can calculate, by means of the angle between the two directions, how high they are above them when they first see them, and at that moment they must have struck against the atmosphere, and even traveled some way through it to become white hot. In this way we have learned that meteors burst into light at least 100 miles above the surface of the earth, and so the atmosphere must be more than 100 miles high. Our next question is as to the weight of our aerial ocean. You will easily understand that all this air weighing down upon the earth must be very heavy, even though